Okay, good morning. So today we're going to be talking more about harmonic perturbations, which we started talking about last time. And so the word harmonic is just a fancy way of saying that the dependence on time is through sines and cosines, or equivalently, things like e to the I omega t. And so we're writing a Hamiltonian, which is a constant part plus a time-dependent part. And so if we turn on our Hamiltonian at time t equals 0, so it's 0 for t less than 0, and we just say, what's the most general harmonic Hamiltonian we can write down, then it's going to be v times e to the I omega t, and something else times e to the minus I omega t. But if the Hamiltonian is going to be Hermitian, which it has to be, then that means that the second thing, v, which I've written as v dagger, has to indeed be the Hermitian conjugate of the first thing, just so that when I take the Hermitian conjugate, I get the same thing back. So that's going to be the Hamiltonian for t greater than or equal to 0. Okay, and then we worked this out last time using the general features of time-dependent perturbation theory at first order. So everything's being done at first order. And we found that it split into two parts. The two parts came about because we had delta functions, and you couldn't have both of the delta functions contribute at the same time. So there are two parts to the transition rate. And today we're going to be calling our starting state I, and we're transitioning to a final state F. And again, remember, these are supposed to be eigenstates of our unperturbed Hamiltonian. So just to have something in mind, our unperturbed Hamiltonian might be, for example, the Hamiltonian that describes electrons in an atom, maybe the hydrogen atom, to make things simple. But then something comes along and disturbs it, maybe an electromagnetic wave. Okay, now before I write these down, I'm going to add one other ingredient that we didn't put in last time, and that is that the final states might be degenerate in energy. So suppose that there is a degeneracy. Remember, degeneracy is just a number that tells you how many states have the same property. In this case, the property is the unperturbed energy eigenvalue, which I'm going to be calling curly E sub f. Okay, and so the degeneracy, we're going to call it little u curly E sub f. That's the number of states that all have the same unperturbed energy, curly E sub f. So in the past, we'd called degeneracy rho sometimes, but we're not going to do that today because rho is going to be something else. Okay, in fact, we're about to write down what that something else is. Okay, so the two parts that we found we called absorption. And so the rate for absorption to go from an initial state, and then we're absorbing an amount of energy h bar omega from the perturbation to go to the final state is, and this is Fermi's golden rule. So there's always a 2 pi over h bar. There's a matrix element of the perturbation, which I'm writing like that for shorthand. There's a delta function, which last time came from a function f that we called f, and then we took the limit in which it approached the delta function. And then there's the density of states, because we have to sum over all possible states that meet our criterion of the delta function energy. So there's our density of states. And then to apply this, we need to sum or integrate over all the energies that we're interested in, and now over all of the degeneracies of the energies that we're interested in. So this rho is defined to be, it's the density of states, which means it's the number of states between energies curly E sub f and the differential of curly E sub f, and between the degeneracy U E sub f and U E sub f plus a differential in it. Okay, and so that was the absorption rate, and then there's an emission rate. Okay, and so this is now initial state going to final state, plus we're donating some energy to the perturbation. And this looked almost the same. The main difference is that instead of the operator V that we're taking the matrix element, we're taking the matrix element of V dagger. And the delta function is slightly different because the h bar omega now has the opposite sign, because instead of stealing energy from the perturbation, we're donating energy to the perturbation. Okay, but then the rest of it's the same. So an interesting thing about these formulas is that sometimes you can get two results for the price of one, or for the effort needed to calculate one of them, because let's say that one of these processes can occur. So suppose it's possible to go from the state I to the state F by emitting energy h bar omega to the perturbation, which in this case will be V dagger. Then it must also be possible, because everything works, meaning the delta functions work and everything else, to go from the final state to the initial state by absorbing the same amount of energy. So now it's from V. So if one process works, then the other process works. And so it's natural to ask, well, can we calculate one and then get the answer for the other one? And the answer is yes. And here's the reason why it works. So in one process, I need to know this matrix element, V dagger IF. And just as a reminder, this is just shorthand notation for I V dagger F as a matrix element. Okay, but now using the rules for taking Hermitian conjugates, I can rewrite this as F V without the dagger I complex conjugate. And so that's VFI star. And so the matrix elements are really the same for all practical purposes, because if we go back up here, we notice I'm taking the complex square of them anyway. So it doesn't matter that I have a complex conjugate sign there. The matrix elements are the same for the two processes. And so what that means is that I can take one of them to be the initial state in one process and the other to be the initial state in the other process. So let's temporarily use a more neutral notation where instead of calling them initial and final, I'm going to call them A and B, because in one process, one of them's the initial, and in the other process, the other one's the initial. So given two states, A and B, each can play the role of initial and final. And so if I go back and I stare at my two formulas here, and I notice that, some of the 2 pi h bars are the same and all that, then I can write down a relation between the two different rates. And that looks like the following. If I take the emission rate to go from A to B, and I divide by the degeneracy differential, and then I multiply by the density of states, that has to be the same as the absorption rate with respect to the differential for its degeneracy to go from B to A times its density of final states. Oops, I think I put the wrong labels on my density of states. This should be, so in every case, it should be the final state density. So this should be A, and this should be B and B. Okay, so it's not quite so simple as just saying the rates are the same. You have to multiply by the densities of states to get equality between the two rates. But for any given system, it may be complicated, but you can work out the densities of states. And so you have a nice relation, which is called detailed balance. And later we'll talk about how Einstein used detailed balance to do a calculation that was almost impossible to conceive of at the time by doing any other method. So just for example, and this is actually the example that Einstein was able to do, you can have a process where you have a state A, maybe a state of some atom, and it transitions to a state B by emitting a photon. And then you can have the state B absorbing a photon and transitioning to the state A. And these are related in a way that to get the details of, you have to know the density of states. So in fact, that kind of process is the next thing we want to study. This is really the main reason for why we want to understand harmonic perturbation theory. So our next task is we would like to find what is a perturbation Hamiltonian, W of t, that describes light interacting with matter or with electrons. So to describe interaction between electric and magnetic fields for light specifically, and electron states. So most of what we're going to say applies to any charged particle, but we're particularly interested in electrons because electron states are where, in the real world, the calculations we're going to describe actually work. Okay, so to do this, the first thing we have to do is figure out what the full Hamiltonian is for an electron in the presence of these fields. And for that, you can go back to what you learned, hopefully in a classical mechanics course or a electromagnetism course. But if you didn't learn it or you don't remember it, let's review by writing it down. The Hamiltonian contains, first of all, a kinetic piece where I'm dividing by twice the mass of the electron. So if there were no electric fields here, I would just write P squared. But if there are electromagnetic fields, the thing I'm supposed to write is P plus E over C times the vector potential A. And then I square the whole thing. So we'll get into a little bit what the remind you what the vector potential is. But then there's also this piece where I have my interaction with the electric potential. So let's label these things. This is the vector potential. This is the electric potential. And then something that's harder to get from classical mechanics is the fact that you can also have electrons interact with magnetic fields through the spin. And the form of that is the following. So what are we going to write down here? Basically, there's only one thing to write down because magnetic field is a vector and spin is a vector. And we need a scalar quantity to come out of it because the Hamiltonian is a scalar quantity. And so kind of the only thing to write down is the magnetic field dotted into the spin. But of course, that doesn't tell you what the factor in front is. And it turns out to be the electron charge divided by the mass times the speed of light. Okay, so B here is the magnetic field. Okay, and then I'm going to write plus dot, 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 which might represent other contributions to the Hamiltonian. That might be, for example, potentials associated with not these magnetic fields, but maybe some other magnetic fields, maybe from some nearby atoms that we're not worried about right now. Okay, now all of these quantities that are coming in here, the vector potential, the electric potential, and the magnetic field, we are going to treat classically, even though that's not quite right. If we were doing this really correctly, we should treat them quantum mechanically too. But for what we're going to do, this is going to be good enough to get the answer. And in fact, if we did treat them quantum mechanically, we would just be doing a lot of stuff that in the end would not affect the answers that we're actually trying to get. Okay, so the next thing we want to do is relate the potentials that appear there to the fields. And so this is something that we learned in an electromagnetism class. So the potentials are related to the fields by the following. The magnetic field is the curl of the vector potential. And the electric field is minus the gradient of the potential. That would be true if we were doing statics. But if we're doing time-dependent fields, there's another factor, minus 1 over the speed of light times the time derivative of the vector potential. Now, perhaps annoying thing is that in almost all quantum mechanics books, they use a different system of units than most electromagnetism books use. And so I'm going to follow the quantum mechanics tradition. And so this is a note on units. In quantum mechanics, we generally use the metric system in centimeters, grams, and seconds, the CGS system. And so Maxwell's equations might look a little bit different than what you're used to. So the divergence of the electric field, for example, in the CGS system is 4 pi rho. Rho is the charge density. But in the SI or MKS metric system, it would have been rho over epsilon naught. So in the CGS system, there's no such thing as epsilon naught. You never talk about it, which in my mind is a good thing. I don't like epsilon naught. I'd rather deal with a nice number like pi. Okay, and rho here is the charge density in either case. Okay, and then in the CGS system, for example, the curl of the electric field, this is Faraday's law, is -1/c, the time derivative of the magnetic field. In the SI system, this is just, you leave off the speed of light factor. In both of them, the divergence of the magnetic field is 0. 0 is great because it doesn't depend on what system of units you're using. And then finally, we have Ampere's law, which says curl of B equals 1/c time derivative of the electric field plus 4π/c times the current density J. So in the SI system of units, this looks like 1/c squared plus mu naught J. So the main difference is that in the CGS system, there's no such thing as epsilon naught on mu naught, which is good. Everything is just pi or the speed of light. Okay, and then the speed of lights go in different places. They're absorbed into the definitions of the fields when you go between the different system of units. So J here is the current density. Okay, so other things that are important besides Maxwell's equations are we're going to want to keep track of where energy is going. So energy density is going to be an important concept. This is the energy per unit volume in electromagnetic fields. And in our CGS units, it's 1/8π E squared plus B squared, which is nice and symmetrical between electric and magnetic fields. Whereas in the MKS system, it's not symmetrical. It looks like this. Okay, and then that's where energy is. And then there's where energy is going. The power per unit area, that's the Poynting vector, which is C/4π E cross B. Okay, and then in the MKS system, that's 1/mu naught E cross B, which always annoys me because why is there a mu naught in that formula and not an epsilon naught? It's again in the CGS system, it's much more symmetrical. So if I was dictator of physics, we would all be using CGS, but unfortunately I'm not. But anyway, another important thing that we want to talk about is gauge transformations. And so gauge transformations tell you that if you're only interested in the electric and magnetic fields, then you can change your potentials at any time you want by taking the electric potential and replacing it by itself plus a time derivative of any function you want. So lambda here is any function of time and space. Absolutely anything you want, provided that at the same time, you do a corresponding change to the vector potential where you subtract the gradient of that function. So as long as you do those two things at the same time, you're okay. No electric fields and magnetic fields change. That's a consequence of these formulas up here. You can just plug into those formulas and check that they don't change if I do a gauge transformation. And for quantum mechanics, at least for what we're going to do, the main impact of this is that we want to choose our gauge very carefully. And the best gauge choice for us, so we can, and I'm going to say and will, choose Coulomb gauge. Other gauge choices are much better for other things, but for what we're doing, we want Coulomb gauge, where in Coulomb gauge, the divergence of the vector potential is chosen to be 0. If it's not 0, you do a gauge transformation to make it 0. So why do we want Coulomb gauge? It's just that it makes things simpler because a certain commutator vanishes. Namely, here's our reason. Since we remember that the momentum operator in three-dimensional space is minus I h bar times the gradient, okay, that means that if we take the commutator of momentum with the vector potential, no matter what the vector potential is, as long as it's in Coulomb gauge, we get 0. And it's just because when I do the commutator, I get the divergence of the vector potential like that. So this is true in Coulomb gauge. And so the reason that's convenient is now I don't have to worry about when I write down things that involve both P and A, I don't have to worry about what order I write them in because they just commute with each other anyway. So going back up to see where this is going to be useful specifically, if I stare at this term and I square that out, there's going to be a term with P in front of A, and there's going to be a term with A in front of P. But those two terms are going to be the same. There's no difference between them because P and A are just going to commute with each other. And so I have one less thing to worry about as far as the ordering of operators. Okay, so we'll see that in just a minute. But first, let's talk about the light waves. Okay, so light is an electromagnetic wave. And in Coulomb gauge, when you're describing such an electromagnetic wave, it has the nice property that the vector potential is itself a wave. It's got some amplitude, A0. There's a cosine k dot r minus omega t. And then there's a polarization vector because it has to have a direction. Okay, so I'm going to be calling curly E the polarization. Omega is the frequency. That's going to be the frequency, the same frequency that goes into our harmonic perturbation. Okay, it's equal to omega. It's equal to k over c. C is the speed of light, and the electric potential in Coulomb gauge is just 0, which is really convenient. Okay, so that term in the Hamiltonian is just going to go away. And then when I do this, I'm going to promote little r the vector to big R the operator. So my vector potential, we were thinking about it classically, but now we're going to promote it to an operator. But it's not, it's an operator that's fixed in terms of the position of the electron that it encounters. Okay, so now we can go ahead and take those and compute the electric and magnetic fields you get from that. And what you will find is that the electric field, which is going to be an operator, is the polarization vector. It's in the same direction as A when you're in Coulomb gauge, not necessarily when you're in other gauges, times E0 times a sine function, because you're taking a derivative. And E0 is related to A0 by a nice simple formula, minus omega over c times A0. And so from now on, we're just going to quote everything in terms of E0, which is the amplitude of the electric field. So it's, in fact, the amplitude of the wave, of the electric field wave. And then the corresponding magnetic field is the direction of propagation k hat cross curly e hat. Same E0 amplitude, and in fact, the same sign factor. Okay, so now we know how to describe, we sort of worked backwards. We wanted to describe this electromagnetic wave, and we're saying in Coulomb gauge, this is how you do it. You write down this vector potential. You're going to promote it to an operator. Okay, and now we can plug that into the Hamiltonian that we wrote down before. So our Hamiltonian is, the first thing I'm going to do is take the thing that involved a momentum and I'm going to square it out, and I get 3 terms from that. So there's p squared over twice the mass of the electron. And then there are 2 terms, so I'm going to write a factor of 2 times E over C, and then there was A dot P and there was P dot A. But remember, in Coulomb gauge, those are the same thing. That's why I got the factor of 2. And then this is also divided by twice the mass of the electron. And then there's 1 over twice the mass of the electron, E squared times A squared. And then there was the term involving the electric potential. And then there was the term involving the spin. Okay, so now we're going to notice that, aha, this term went away in Coulomb gauge. That's a special feature of both Coulomb gauge and the fact that we're talking about an electromagnetic wave. For other configurations that aren't just electromagnetic waves, we would have to worry about that term. And we're also going to throw away this term, only because it's going to be small. We're going to neglect this, assuming that it's small. So it turns out if that term isn't small, you have to do some fancy other stuff anyway to get everything to work. So what's left? What's left is the first term, which we're going to call our unperturbed Hamiltonian. And then the 2 surviving remaining terms here are going to be our perturbation. Hidden in that is the fact that A and B both depend on time harmonically. And so this is a great example of a harmonic perturbation. Okay, questions on any of this so far? Okay, so let's write our W of t. It's got 2 terms that both have the electric field over MEC in them. And those 2 terms are A dot P minus B dot S. And so now the next thing to do is just plug in what they are as functions of time. So both A and B had a factor of the electric field amplitude in them. And then the first term was minus cosine k dot r minus omega t. I've promoted r to an operator now. And that's the momentum operator. And then the second term has plus, the minus signs cancel actually, sine k dot r minus omega t. And then there's k hat cross my polarization vector dotted into the spin. Okay, and so that's the whole thing. And so without doing anything else, we can notice this is indeed a harmonic perturbation. So we can, for sure, write it this way. Okay, and if you work it out, you find out that what the operator V is, it's the following. So this is something that's independent of time, and it's minus E0 over 2 ME omega. And you can write it as the polarization of the wave dotted into e to the I k dot r times p minus I k cross the spin. Okay, that's within the approximation that we've made that we can throw away the vector potential squared as being small. Okay, so that's our V, and now we can take matrix elements of that and use what we found for absorption and emission of it in the general case. So to do that, we're going to first give this stuff in square brackets a name. We're going to call this curly P. Notice it's a vector, and it also depends on a vector. It depends on K. Okay, and so this also depends on the momentum, sorry, the position and the momentum of the electrons, or the electron in the state we're talking about. That is the state that we're going to take matrix elements of. So some things to notice about this thing: it has units of momentum. And not only does it have units of momentum, it actually is approximately equal to the momentum if k is small. And that approximation, where k is small, is known as the dipole approximation. But we're going to try to be as general as possible by not specializing to the dipole approximation until we absolutely have to. And so what we'll be doing is just writing everything in terms of this curly P sub k. And then when we want to take the dipole approximation, we will plug in that it's P. Okay, so now we're all set up. We're ready to do absorption and emission of light by atoms and other electronic systems. So let's go ahead and do that, starting with absorption. So we're going to talk about absorption of light. And so we're going to start with an initial electronic state. Which we'll call I, and a final electronic state, which we will call F, and F is characterized by its energy and its degeneracy of the energy in the unperturbed Hamiltonian. Okay, now we've already worked out what the answer is. That's Fermi's golden rule for absorption. So Fermi's golden rule tells us the differential rate, gamma's for rate, for absorption to go from the initial state plus a photon of energy h bar omega to the final state is our usual 2 pi over h bar. And now we just have to write down this factor here that occurs in our perturbation Hamiltonian. And this matrix element's going to get squared. So I'm going to get a factor of this squared. Okay, so this is little e electric field over twice the mass of the electron times the frequency, all squared. So we've taken care of that part. Then I have the rest of my matrix element, which is the matrix element of the polarization dotted into my curly P operator. Okay, and then that's it, except for the density of states factors. So I have to write those down, and I have to write my delta function. And finally, my differential of energy. Okay, so that's progress. But now the thing is, that's not a number that you can measure in an experiment, because it's got a delta function in it and it's got these differentials. So we want to ask, how do we get a measurable number from this formula? So one thing we're going to want to do is integrate over energy to get rid of the delta function. But more generally, it's a good idea often to quote things not in terms of the rate, but how much energy is absorbed. So I send in some light wave, it encounters some atoms, and then I measure how much energy is absorbed, and that's something we can measure. So to do that, let's consider first the energy that's present in the initial beam of light that I send in. Energy flux in the light wave. Okay, otherwise now flux means per unit time per unit area. So this is energy per time per area. Okay, and that's equal to the speed of light times the energy per volume, which we called before little u. So this is energy per volume. And then because the light is moving at the speed of light, we multiply that by the speed of light to get the energy per unit time per unit area. Okay, but now for an electromagnetic wave, this is just E0 squared over 8 pi. So if we stare at that, we realize a nice fact. The energy flux that's present in the wave we sent in is proportional to E0 squared. And the rate for transitions is proportional to E0 squared, which makes sense. If we make E0 bigger, then we should get more transitions. And so because they're proportional, it's a good idea to just define their constant of proportionality. So absorption rate is proportional to the energy flux in the light. And so now we define their ratio. The letter traditionally used for this is a lowercase sigma. This is the cross section. So this is absorbed energy per unit time divided by energy flux in the wave. Okay, and this has units of area. Cross sections always have units of area, and that's what this thing is. This is a cross section. Okay, and so intuitively you have your atom sitting here minding its own business. And some light comes along. And if the light just misses the atom, it just continues going. But some of the light is going to encounter the atom and get absorbed, and the amount that will get absorbed is proportional to that area. It's not equal to the area of the atom, but it's proportional to it, because some of the light will just make it through without interacting with the atom. But that's why the cross section has units of area. Okay, so this cross section is the effective area of absorption. Okay, and so what that means is we're going to now write, instead of the differential of rate, we're going to write the differential of cross-section, which is something that you'll see quoted in experiments. And so what's that going to be? It's going to be h bar omega times the differential in rate divided by this energy flux, which was speed of light E0 squared over 8 pi. So the meaning of the numerator here is the h bar omega is the energy per absorption, because each photon that we absorb has that amount of energy. And this is the rate of absorption. And so the product of them is the energy per unit time. So in this quantity, E0 is canceled out between the numerator and denominator. And so that's good, because then you don't have to quote an answer for this. The experimentalist doesn't need to tell you exactly to, so many significant digits, how much energy they had in their laser beam, let's say. The other thing we're going to do is we're going to write this in terms of the fine structure constant. That's just traditional to do. The fine structure constant is charge on the electron squared divided by h bar c. So why is it written in terms of the fine structure constant? Let's go way back up to our formula here. We've gotten rid of the E0 part by taking this ratio that's called the cross-section, and what's left is proportional to E squared. And so that's proportional to the fine structure constant. Okay, so summarizing what we've got, our differential cross-section for absorption is equal to, when you work out the 4 pi's and stuff, it's 4 pi squared fine structure constant h bar over the mass of the electron squared times the frequency. We still have a matrix element to compute. We haven't been really talking about that, but eventually we'll have to worry about that. And then we have our density of states factor, which is the same as it was before. And we have our delta function. And we have our differential of energy. Okay, so now what are we going to do? The next thing we can do is we can integrate over the final state energies, and all that's going to do is turn this last factor into 1, because when you integrate a delta function with respect to that variable, you just get 1. So we can integrate over final state energies, and those two factors just go away and give 1, except that provided, you have to remember that when you do that, then you must set E final equal to E initial plus h bar omega. Okay, so, and remember that now this must be true. So everywhere you see an E final, you can plug in E initial plus h bar omega. Okay, so just to write this one more way, we now have our differential cross-section is 4 pi squared fine structure constant h bar over me squared omega. We have our matrix element squared that I'm not going to rewrite. We have our density of states. Oops. We still have our differential with respect to the degeneracy. So that we're going to have to integrate or sum over on a case-by-case basis once we've decided what our final states are. Okay, and then the other thing to remember is this omega here is now fixed. It must be the final state minus the initial state divided by h bar. So you can't just, when you plug this in, you have to plug in that as the fixed omega that contributes to this process. Okay, so that's what you get if this is if the energies that we integrated over are continuous. Now there's a formula like this in the case where the final states are discrete instead of continuous, but we'll talk about that next time because we're out of time for today. Okay, so tomorrow, I believe, is the final due date for the homework, which has gotten postponed a couple of times. And I want to remind you that the price you paid for having extra time to work on that is now there's another homework set that's due a week from tomorrow, which is not necessarily the shortest homework assignment ever. So make sure that you do not put that one off for the last minute. All right, any questions on today's lecture?
I have a question on the homework.
Okay, so let me stop the recording and then we'll talk about that.